thanks very much for the introduction. And well, it's a great pleasure to be back in Frankfurt virtually. Would have been, of course, a greater pleasure to be there in person, but yeah. Sorry. So this will happen quite a bit. I apologize for that in advance, but this also means that for me, it's probably better to have this virtually than in person. Right. So I will talk about joint work with Amnon Besser and Padmavathi Srinivasan. And well, I should say that there won't be that much non-Archimedean and probably no tropical geometry in here, so I also apologize for that, but well, it is what it is. I'll say a few words in that direction. Well, I guess the title features the word P-adic, so maybe that's already good. Right, so the goal of this talk will be to explain a new construction of P-adic heights, specifically on abelian varieties, but also in a way more general setting, and how to apply that to give a new construction of the Quadratic Chabauty method, which is a method for computing rational points on homogeneous curves. So I'll start with that. So here's the rough outline. So I'll introduce what I want to do and also talk a bit about motivation. And then I'll, well, then comes sort of the technical part. So I'll introduce what I mean by P-adic Arakelov theory. So this is not the same as non-Archimedean Arakelov theory. It's an unfortunate clash of words, whereas, you know, non-Archimedean Arakelov theory is typically real valued. P-adic Arakelov theory takes values in the P-adics. Okay, and well, this is a theory going back to Amnon Besser about 15 or 16 years ago, or maybe even earlier than that, but we will focus on the case of abelian varieties, which is sort of new. And then I'll show how to sort of reconstruct Quadratic Chabauty in what we think is a much simpler way. Right. So let's start. So this was our motivation, was to give a new construction of the Quadratic Chabauty method. So let me say something about that. So this is the sort of research that I typically work on, is sort of explicit methods in rational points. And here we have the very simple situation of a nice curve over the rationals of genus G greater than 1, where throughout this talk, nice is going to mean smooth projective and geometrically integral. And well, I'll work over the rationals for simplicity and also to spare myself the embarrassment of getting some local constants wrong, which would inevitably happen. So J is going to denote the Jacobian of X, and the goal is to compute the rational points on X. Now, by Falting's theorem, we know that there are only finitely many of these, but there's still no algorithm, no effective methods that will always compute the rational points. And you know, so we've got a bag of tricks that we could try to apply, but in general, this is a very difficult problem. And so one of the sort of most successful techniques is the method of Chabauty and Coleman. And well, in a nutshell, this is what comes out of it. So the idea is you take a prime and you somehow want to identify the rational points among the P-adic points on the curve. And well, actually everything takes place in the P-adic points on the Jacobian. And so if you assume that the rank of the Mordell group of the Jacobian is less than the genus, then what you can show is that there is a locally analytic function f on the P-adic points that only has finitely many zeros and that vanishes in the rational points. Yeah, and so this is somehow by working inside of J of QP. I won't go into detail here, but so a lot of work has gone into trying to extend that to all nice curves of genus greater than 1, right? Because we have this condition that the Mordell rank is less than the genus. And while for a random curve, whatever that means, we would typically expect this to hold, for many interesting curves, this does not tend to hold, especially for modular curves, right? So, this is a very restrictive condition. Okay, so there's this program of Min-Young Kim to generalize Chabauty's method in a non-abelian way. And well, there has been quite a bit of theoretical progress in this direction, but it's very difficult to turn this theoretical progress into actual explicit methods, which is what I'm asking for here, right? So when I say compute X of Q, I mean, I really want to compute this in practice. And one of the reasons is that Kim's program uses anabelian geometry and P-adic Hodge theory, which in itself is, you know, quite far away from explicit methods. But there is a situation where this has been made explicit, and that's the Quadratic Chabauty situation. So this, I'll just summarize this here. So this technique is in this form due to Balakrishnan and Dogra. And they show that you can extend this Chabauty-Coleman method in that you get this, you can write down this locally analytic function that vanishes in the rational points if the Modivari rank is equal to the genus. So it's sort of the first non-trivial case beyond classical Chabauty. And there are some additional conditions which I will come back to later when I explain our new approach to this. But so this is fairly restrictive, but it is set, these conditions are satisfied for some interesting curves. And so the ingredients are that you apply the non-abelian Chabauty method of Kim. You combine the non-abelian Chabauty method of Kim together with Nekovar's work on P-adic height functions. Yeah, so in the end, the rough idea is that non-abelian Chabauty tells you that there, in this situation that we're considering here, there should be some quadratic relations between certain P-adic integrals, and the P-adic height is a quadratic form, so that somehow realizes these quadratic relations in a way that leads to actual explicit methods. And well, there are many different constructions of P-adic heights, but Nekovar's construction is in terms of P-adic Hodge theory, and so is Kim's non-abelian Chabauty. So that's why this is the way to go here for this kind of approach. But I'll show you that there's a different one. All right, and so this can be applied in practice. So here's some explicit results. So together with Krishnan and Dogra and Trautmann and Vonk, we found the rational points on some modular curves of interest. So, well, I mean, here are just some numbers. So in the first one, there are 7 rational points. So this is the non-split or split, which in this case is the same thing up to isomorphism. Level 13 Cartan modular curve. Yeah, and so this curve satisfies all the conditions that the quadratic Chabauty method has. In particular, it is rank equal to the genus and both equal to 3. And so recently we found the rational points on some other curves with sort of similar techniques. And so the largest genus we can do in practice right now is 6. It's already quite computationally challenging. All right, now I should mention here that there's yet another approach to quadratic Chabauty, which is due to Bas-Edixhofen and Guido-Lido, which is very nice, but which for lack of time, I won't talk about here. Right, so I mentioned the P-adic height here. So let's say something about the P-adic height, since that is somehow the main ingredient for the quadratic Chabauty method and also the main topic of this talk. So more generally, I'll let A be an abelian variety over the rationals. And I fix a prime of good reduction P, and I want good reduction sort of for simplicity. Everything we do can be generalized to other types of reductions, so then it's harder to actually compute things. And so there's a global P-adic height pairing HP on A cross A dual into QP, which is a bilinear pairing, which you should think of, if you haven't seen it before, as some P-adic analog in the sense of the canonical or Néron-Tate height pairing, which here I denote by H infinity, and which is real valued. And well, it's somewhat analogous because there's no kind of, dynamical, no Northcott properties, and that, doesn't really make sense in the P-adic world. But it is a bilinear pairing, and it's analogous in the sense that many constructions of the canonical height pairing also work to construct a P-adic height pairing. Well, you have to change them a little bit. And so what I want to talk about today, first an important remark. So maybe for this audience, that's not necessary, since I assume most of you think P-adically anyway. Yeah, so this pairing HP, this is a global pairing that takes values in QP. Yeah, and so it's not the local component of the real valued Néron-Tate or canonical height pairing at P. Yeah, so I tend to get this question a lot at talks. So these are 2 completely different things. Well, not quite, we'll see. But yeah, so the constructions are fairly similar, the constructions that are known, and this talk is no exception. So I will give a new construction of P-adic heights using Adelic metrics with values in QP. And so this is similar to, well, a well-known construction of the canonical height using Adelic metrics, which I'll summarize in a minute. And then I'll talk about our main application, and that's a simpler approach to quadratic Chabauty. All right, so, well, let's talk about real valued metrics. So in case you've seen this sort of thing before. If you haven't, then can tune out for a couple of minutes. So yeah, in the real valued setting, you can actually construct the canonical height. I mean, this sort of goes back to Néron by looking at a local decomposition. And one way to do this is by using a local decomposition in terms of metrics. Yeah, so I think this definition is due to Zhang. So an Adelic metrized line bundle, L bar, is as follows. And again, I'm restricting to a specific situation. So you need a line bundle L over a nice variety X over Q. So remember, nice was smooth projective and geometrically integral. And then for each place of Q, you fix a real valued metric on L, or rather on L tensor QV. And here a metric is just a norm on each fiber of L. Yeah, so it's a family of norms. And there are some additional conditions here that I want to sweep under the rug, because I mean, this is just for way of analogy that I'm summarizing this here. Okay, and so once you fix this sort of data, you can define a height on L. Oh, sorry, a height with respect to L, which depends on the choices of metrics. And so you do this as follows. So suppose you start with a rational point X, then, well, you just pick some vector U, some non-zero vector on L above X in the fiber above X. And then the height of X with respect to this Adelic metrized line bundle, it has a very simple definition. Yeah, it has this local decomposition. So you just take the norm of U at V, take its logarithm, and then sum over all places. Yeah, and so that gives you a real number. And you can show that you can recover sort of more classical definitions of heights, of real valued heights in this sense, in this way. Okay, and so the setting that we really care about is that of an abelian variety, where you put an extra condition on all of these metrics. Yeah, so they're called canonical, and I'll come back to that. But in that case, you actually recover the canonical height of the Néron-Tate height function with respect to L. And so that's what we want to do in the P-adic world. And by the way, notice that this height is actually well defined. If you take a different vector, then it means you change U by a scalar, and then, well, that scalar, well, I should say the log of the norm of that scalar then will pop out additively, and by the product formula will disappear. So this height is independent of the choice of U. All right, so our goal for today is to give a P-adic analog of this. And so we need P-adic analogs of the height, but also of these metrics. But notice that what actually goes into the height is not the metric itself, but rather the logarithm of the metric. And that will actually be important. So that's what we want to analogs of. All right, so to do that, to find these, sorry, just a second. To find these analogs of logarithms of metrics and of heights with values in QP, well, let's go backwards. Let's first think about what I just said was, and that was that we need the product formula to have a height that's well defined. And so we need a P-adic version of the product formula, and you just do the usual thing. You fix a continuous ideal class character chi with values in QP. Now, of course, for Q, there aren't a lot of these, but like I said, everything I do here extends over number fields, and then there are actually choices, and it's interesting also to see what happens when you take different choices and maybe combine them. Right, so we're going to fix this choice. And here's what we want. So the terms here don't make sense yet, but they will. So what we want to do is to start with a point X, a rational point on big X. Then I pick again a vector U on L above X, a non-zero one. And then the height is going to be of this form, the P-adic height. Well, there's a first term, which is a function log LP of U. So this is somehow the contribution at P. And that's going to be a Coleman function. This log LP, and then there are the contributions away from P, and here away from P means at other primes Q. So Q runs through all prime numbers that aren't P, and well, for pretty obvious reasons, there's no Archimedean contribution here that we have to consider. Right, and so what are these VLQs? Well, it turns out that for that we don't need any new theory. So VLQ of U, that's going to be a rational number, which is good because rational numbers are P-adic numbers. So then this rational number times chi Q of Q, which is a sort of weighing factor so that you get an analog of the product formula, and so you get something well defined on X that doesn't depend on U. Yeah, so this VLQ of U is a rational number that pops out of the classical theory already. More precisely, it's going to be more or less the same as the logarithm of the norm of U, where this is the norm coming from a real valued metric. Yeah, and so this, by more or less, I mean it's up to a constant, right? Because this log norm of U, that's going to be a real number, but we want a rational number. But yeah, and then it's also it's not clear that this will work for all real valued metrics, and it doesn't. But for the ones that that you tend to come across, this actually holds. All right, so this is what I want to define in this talk. Yeah, and I'll start with what's going on at Q away from P, because, like I said, that's somehow similar to the classical theory. And then for log LP, we're going to need some P-adic analysis. And so, yeah, any questions at this point? All right. So let me continue. Excuse me. So, all right, P-adic Arakelov non-abelian varieties, starting with the easy bits. Yeah, so for now, Q is going to be a finite prime not equal to P, and X is going to be a nice variety over QQ. Again, you can do things much more generally. I'll let L be a line bundle on X, and I'll sort of, in the back of my mind, I'll rigidify it. I won't really spell this out because I want to keep the exposition somewhat simple. But we'll see when we talk about abelian varieties why this is actually important. All right, and so this line bundle induces a GM torso, which I'm going to denote by L star, and that's just a total space without the zero section. Yeah, and remember, we're interested in something that should be an analog of the log of a metric. Yeah, and so that is actually defined on L star. So this is the sort of space we should consider. Yeah, and now I'm going to call a function V on L star into Q. So I want this, and this is important. So this is supposed to have rational values. I'm going to call this evaluation on L if this scaling condition here is satisfied. Yeah, so so U is going to live in some fiber, and then I can scale U by some lambda using the GM action, and then then V of lambda of U is supposed to be V of U up to this this valuation of lambda. Yeah, and so if you think about it, that's precisely, although I haven't written it down, but that's precisely the sort of behavior you have for real valued metrics on L. Yeah, so or rather for the logarithm of that, right? Because you write the metrics as families of norms, so you write them multiplicatively, but we're taking the logarithm. Yeah, so if you start with a real valued metric, which takes values in, well, Q to the Q, so the values should be of the form Q to the rational number to the A, where A is a rational number, then I can actually get a valuation and as follows. So I take the logarithm of the norm of U, and then, well, I just make this number rational by dividing by log Q. Right, and so this seems kind of contrived, but it turns out that this actually works. That this actually works for many metrics that we care about, right? But I sort of chose to introduce valuation that's rather than metrics here. All right, and then you have kind of obvious notions of pullbacks and tensor products, and also you can talk about isometries. Well, I should say isometries of metrized or maybe valuated line bundles here. Yeah, so you can, if you have an isomorphism between line bundles and you put valuations on both of them, then there's a notion of isometry, just like for classical metrics on line bundles. All right, so let's look at a couple of examples. Again, this is all classical. You can find this for instance, in the book on heights and Diophantine geometry by Bombieri and Gubler. So, for instance, I mean, how do you get valuations, for instance, using models? And so, given the audience here, maybe I should talk about how you get models from, how you get valuations from formal models, or just in terms of Berkovich theory. But I mean, I won't do that here. So this is just the simplest situation. So if I take a proper flat and integral model, curly X of my variety X, and I extend L to a line bundle curly L, yeah, I can, if I have a rational point, a QQ rational point on X, then I can of course also take the corresponding section of curly X. Yeah, and then I fix some section S of L, which doesn't vanish in 0 or infinity. Yeah, and then the choice of my curly L will now define a valuation as follows. I mean, the valuation of S of X, yeah, which lives in L star, where it's supposed to live, that's going to be the valuation of the pullback of S by X with respect to this lattice X bar per star of L. Yeah, so X bar, sorry. Yeah, so this X bar per star of L gives me a lattice in, well, normal X upper star of L. Yeah, and then I could take the valuation of the pullback of this rational section with respect to this lattice. Yeah, and so this is somehow taking place with respect to a projective rank 1 modulo over ZQ. Well, there are other ways to write this down, but I mean, so this defines a valuation, which is somehow very classical object, and we can call this a model valuation. Yeah, and like I said, you can do this for using formal models and using, you know, much more involved constructions, but if you're interested in that, you shouldn't ask me, you should ask the next speaker, because Klaus knows a lot more about that than I do. Right, oh yeah, and I say metrics induced by formal models, so I mean valuations, but yeah, I mean, in this way you can define metrics or valuations. They're analogous in this sense. Okay, and so let's talk about abelian varieties. I mentioned before that in Zhang's construction of the canonical height using Adelic metrics, he had this condition that the metrics were supposed to be canonical. So what does that mean here in terms of valuations? If A is an abelian variety and L is a line bundle on A, yeah. So for now, let's restrict to even, by which I mean symmetric or odd, anti-symmetric line bundles, which I rigidify by, I mean, let's just rigidify them at the origin. Then I call a valuation on L canonical if this isomorphism here, where K is either 4 or 2, depending on whether L is even or odd, is an isometry, yeah, for the induced valuations, right? Evaluation on L by pullback or tensor product constructions gives me valuations on both sides, and I want this to be an isometry, right? And I chose a rigidification because I want well, I want n isomorphism here, yeah. So this is induced by my choice of rigidification. Okay, and then the question is, does this exist? And the answer is yes. And again, in the book by Bombieri and Gubler, you can find a construction of this. And I guess this is also in earlier work, for instance, by Zhang. And well, I mean, the way to construct this, for instance, is just using sort of Tate limit construction. And then here, because we talk about valuations, which in particular are Q-valued, you also have to show that you actually get something Q-valued using this construction, which maybe it's not immediately obvious, but for instance, if you reinterpret these metrics in terms of, well, intersection multiplicities on Néron models, then you get this at once. All right, and just as a side remark, for the people in the audience who care more about Berkowitz theory or tropical geometry, which should be a large part of the audience given the theme of the workshop, well, these canonical evaluations can be interpreted in this way. And so there are examples in papers by Gubler and Kuhnemann and by Zhang and Chokre. And I think, I mean, from what I understand, these expressions should be more or less equivalent to each other. All right, so let's see. So this is a good place to reflect on what we have been doing. Okay, so we have now we have valuations at places away from P. We have canonical valuations on abelian varieties at places away from P. So that gives us the summons in the contributions to our global P-adic height at places away from P. So what remains is to discuss the contribution at P. And like I said, that is done using P-adic analysis, more precisely P-adic integration. And I'll be sort of vague in some of what I said. So I apologize for that in advance. Right, so here, from now on, for the rest of this part of the talk, until I say otherwise, X is going to be a smooth and geometrically connected variety over QP. And I will fix a branch of the P-adic logarithm, because the integrals I will talk about, and then also several notions I will define will actually depend on the choice of this branch. But you can choose any branch you want. So there's a notion of P-adic integrals. Well, there are many notions of P-adic integrals in various degrees of generality, and using various different types of machinery, which I don't want to go into detail here, but I mean, the idea is that if you have a closed differential form on X, then you should be able to integrate that somehow. And well, locally, that's somewhat easy to do, right? I mean, so for instance, say if you're on a residue disk or something like that, or residue multi-disk, then you can take your differential, expand it into a convergent power series, and then just integrate termwise. So that's what you always do, what you always also do in complex or real analysis. The problem here is, as I don't need to tell this audience, there's no good notion of analytic continuation, at least not without introducing further machinery, right? And so you need somehow a different way to set the global constant of integration. And so the way Coleman did this classically, and the way that you can still translate these constructions into actual algorithms to compute these integrals, which is, for explicit methods very important, is to impose a compatibility with Frobenius. Yeah, and so like I said, I'll mostly focus on this construction by Coleman, but there, all of these other names here have also defined P-adic integrals in greater degrees of generality. Yeah, so here's a very simple example. What do I mean by imposing compatibility with Frobenius? So just fix the coordinate z on, well, a1 minus 0. So then I want to see why in Coleman's approach, where you impose somehow compatibility with Frobenius, you should have that the integral of dz over z is the P-adic logarithm of z plus a global constant, right? So I want that this is a global constant, and then you can just assume that it is 0 just by sort of redefining. So then locally, this is very easy. Again, just expanding into power series and then looking at the definition of log QP. But now we want to globalize. I want to say that I can choose the same constant c sort of for all disks if you want, right? If I cover A1, that's the origin with this. And I do that by requiring that acting on the integral of dz over z by Frobenius should be the same, well, up to a global constant, as acting as the integral of Frobenius upper star of dz over z. Yeah, but I know what this is, and it's just p times dz over z. And so I get this condition here that Frobenius acting on the integral of dz over z should be p times dz over z plus c. Okay, great. Well, now, yeah, to turn this into the statement that I want, I just have to look at, say, one point in each disk, where, for instance, I don't know, you can take a root of unity, yeah, you can take a Teichmüller point, and then you see that this must hold. Okay, so that's somehow the easiest example. Sort of on the other end of the spectrum, very specifically for an abelian variety, one way in which integrals arise is if you want to write down the abelian logarithm from a of qp into, well, the tangent space at the origin. So this is somehow the abelian logarithm in, well, viewing a of qp as a P-adic Lie group. Yeah, and that is an integral, or can be described as an integral. So you map a point x to the functional that takes a differential to the integral of the differential from 0 to x. Excuse me. So those are two examples for integrals. So yeah, sorry. So maybe going back, well, now we only saw two examples of single integrals, but you can also talk about iterated integrals. And like I said, I'm trying to keep this basic. If you want to talk about iterated integrals, then at some point it makes a lot of sense to redefine all of this. For instance, using a Tanakian approach, using unipotent isocrystals, which is another setting that might be more to some people's liking. but I just want to keep it simple here and also closer to what we're actually doing in explicit situations. All right, so I'm not going to give a precise definition of a Coleman function, but it is a Coleman function in X is a locally analytic function from X of QP to QP that vaguely looks like an iterated integral locally. So that's enough for us here in for this talk. And so this is sort of looks like a side remark here, but we'll crucially need this in a second. You can define del-bar operators in the setting. So this is due to Besser. Yeah, so if you have a form of the type omega integral eta, yeah, then you just define del-bar of that to be the class of eta tensor omega. And so this lives in this weird space H1 Durham tensor omega 1. And this space will make quite a few appearances on the next few slides. So keep that in mind. So that's somehow the image of the del-bar operator on these type of forms, omega integral eta. But yeah, I mean, this is sort of a local definition. You can define a subspace of Coleman differential forms that's more or less, well, the condition to be in the subspace more or less amounts to saying that locally the form should look like omega, like a form of the type omega integral eta. And then you can show that this del-bar operator, the definition of this del-bar operator actually globalizes. Yeah, so this is how to think of this operator. All right, so remember what we want to do was to define a sort of an analog in using a p-adic analytic method of our valuations. Yeah, so p-adic analogs of the valuation VLQ. And the definition comes now. So a log function on a line bundle L over X. Yeah, so that's going to be a Coleman function log L, satisfying two conditions. The first condition is that it scales in the right way. And by that I mean, yeah, so if you start with a point on X, you lift it to some vector, a non-zero vector in the fiber above X. Yeah, then if you scale that vector by lambda, and this is the same behavior we had earlier for valuations, but what pops out now is the p-adic logarithm of lambda. And if you think about it, that's because, well, if you choose if the local component at P of the chosen ideal class character is this log QP, as we will impose later, then this will tell you that the height we want to define is actually independent of the choice of view. Yeah, and so this is very much analogous to valuations. And there's a second technical condition, which, well, I didn't spell out, but it amounts to saying that this del-bar operator is well defined when you take d log L. Yeah, so d log L is going to be a Coleman function, a Coleman differential form, and this will then live in this subspace where del-bar is defined. And we'll see why this works, why this is important in a second. All right, and so you can build a whole theory using these log functions, they're functorial. And so what Besser did 15 years ago was to essentially redo Falting's calculus on arithmetic surfaces, which is some one-dimensional Arakelov theory in a p-adic setting. Yeah, and whereas here now we want to go to abelian varieties. All right, so these are going to be the functions we care about. However, it's not clear at all that these functions exist, and how unique are they? How can you isolate a canonical log function on abelian varieties? So those are the questions I want to talk about. All right, so the tool for that will be the curvature form. So I will show that there's a curvature form associated to log functions, or maybe if you want to the line bundle together with the log functions, it's closer to the classical theory. And so this is something that in sort of in the complex theory is it's all well known. In non-Archimedean analysis or non-Archimedean Arakelov theory, this is actually quite difficult to construct these curvature forms, but here in this p-adic Arakelov theory setting, they're sort of built into the theory. But I need a strong condition here. So I'm going to take a line bundle L again on my nice variety X over QP, and I have this pretty strange condition. I want the first term class of L, which lives in H2 Durham. I want this to be in the image of the cup product on this weird space H1 tensor omega 1. And well, why this is a weird condition, well, you've seen H1 tensor omega 1 just a second ago, and this has to do with the del bar operator. Yeah, so you can already maybe see where this is going. Yeah, we want to have a curvature from, this is related to del bar d rather than del bar or del bar del. So we're following Amnon and Besser's notation here. Yeah, and so for that we need this condition. Okay, so here's the main theorem about log functions, part 1, part A. For every log function log L, you can define a curvature form. So this curve log L lives in this space H1 tends to omega 1, and it has the property that del bar D log L. Yeah, so D log L, we said, has the property for all log functions that you can define del bar on it. So the left-hand side makes sense, and the property is that this should be the same as the pullback of the curvature of log L to x, right? Because the left-hand side sort of lives on x, and so the right-hand side should live on x as well. Yeah, so there's a unique element with this property, and we call this the curvature form. And well, there are functor reality results about it. And here's the relation to the first Chern class. So it cups to the first Chern class, and this is why we need the first Chern class to be in this strange space. Okay, and so the once you fix a log function, you get a curvature form, and now the question is, can you go the other way around, right? I mean, what happens if you take an element in H1 tensor omega 1, which cups to the first Chern class? Yeah, so we've taken alpha like that, and what you get is that there is a log function having that curvature. Yeah, so whose curvature is exactly equal to this alpha. And this actually, if you look at the proof, it's sort of constructive. It actually tells you how to construct it starting from alpha, right? And so this is uniquely determined up to the integral of the pullback of an omega. But I'm just looking at the time, and I'm going to speed up a little bit. I've been rambling a bit too much. Yeah, but so these aren't unique, but we know what the degree of freedom is, and this is important. So here's a quick example. So if you have a curve, and alpha is a curvature form in H1 tensor omega 1, so it can be written like so, then the iterated integral, or the sum of the iterated integrals of the eta i's and omega i's, already give you a log function. Yeah, so the left-hand side, well, this is something that lives on x. Now the right-hand side lives on, or at least this part here lives on L. Sorry, log L lives on L. So the left-hand side is equal to log L composed with a section S. So S is some meromorphic section here. Yeah, so this here makes sense. And then again, there's this degree of freedom that I talked about earlier. Yeah, so on curves, it's very explicit. Once you have the curvature form, you can already write down a log function. If you don't care which one you want, you can write down a log function. All right, so let's talk about abelian varieties. So now I'm not going to start right away with canonical log function. I'll first talk about good log functions, because it turns out that the condition we want doesn't narrow down the log function uniquely. But again, I will restrict to even or odd rigidified line bundles L on an abelian variety over QP. And so I'm going to call a log function for such an L good if these isomorphisms here are an isometry. Just as before. So I didn't say this, but for log functions, there's a natural notion of isometries. And so here's the first main theorem that we have, namely, if you restrict to even, again, symmetric line bundles, then for every curvature form, so every alpha cupping to the first Chern class, there is a unique good log function having that curvature, right? So there's not a sort of unique good log function for every L, like in the classical setting, but once you've also fixed the curvature, then there's this unique good log function. Great. Now for odd line bundles, the situation is very different. Yeah, namely, if the curvature of log L is, so if you have a log function, then it is good if and only if its curvature is equal to 0, right? So I mean, L being an odd line bundle, yeah, I mean, you can take any alpha that cups to 0, yeah, but you really need alpha itself to be 0 to get a good log function. But once you do that, then every log function is going to be good. So this notion of goodness doesn't really help us too much if we want to isolate canonical log functions, as we will do now. So we have to we have to do this in a different way. If we want a nice theory, we need some kind of other way to isolate good log functions, or to normalize good log functions. And on abelian varieties, if you sort of have too much freedom and you want some universal construction, then it's typically a good idea to look at the Poincaré bundle, which is what we're doing here. So that's going to save us. So we want canonical good log functions, and we get them as follows. So we look at the Poincaré bundle P on A cross A dual, suitably normalized. That is even, so we get a good log function, and yeah, we let alpha be its curvature. So so for every such alpha, there's a unique good log function log P having the curvature. That's what I just said on the previous slide. So we do that here. And then we can use that to define log functions on all line bundles. Yeah, so if L is even, then I can use pullback from the Poincaré bundle to define a log function. If L is odd, then I can restrict the Poincaré bundle to recover L, or at least the line bundle isomorphic to L, and then I can use that to define log L in terms of log P. Yeah, and so for general line bundles on A, well, I can just use A and B and additivity, right? Because I can write any line bundle as the tensor product of an even and an odd line bundle. Excuse me. So that gives us a way to define log functions log L for all line bundles, except that we don't know that this gives us good log functions, right? So this is a canonical way once we fix alpha, but we don't know whether it's good. And then we proved a result that there are curvature forms alpha such that going through this process gives us good log functions on all even and odd line bundles. And well, there are actually many of them. We call these curvature forms alpha good, and the corresponding log functions will be called alpha canonical. Yeah, and so in what follows, we will fix the choice of such an alpha, and then we can talk about canonical log functions. Maybe as a side remark, so these alphas are in one-to-one correspondence with splittings of the Hodge filtration. Yeah, so it means that our definitions of the height will have the same sort of ingredients that other constructions of P-adic heights have. You fix a splitting of the Hodge filtration, and you fix an Adel class character. And this is how the splitting shows up. It gives us a curvature from alpha. All right, so now we can finally define P-adic Adelic metrized line bundles on nice varieties first. So they're given as follows. We have so now we're back in the global setting, right? We want something Adelic. So X over Q is a nice variety. L is a line bundle on X, and then, well, we choose a log function log LP. So that's our contribution at P. And then for every Q not equal to P, we choose a valuation. Yeah. And then there's a compatibility condition, which says that almost all of these valuations should come from the same global model of L. And this is the same compatibility condition that Zhang had. Let's not talk more about that. But once I have this Adelic metrized line bundle, I can finally define a P-adic height, and this is the same that we had earlier. So now I can make do on my promise. So we define P-adic heights once we fix an Adel class character, but now we also want that the component at P is equal to log QP, and that's to make things independent of U. Then the P-adic height of a point X with respect to this Adelic metrized line bundle is just given by choosing a vector U in the fiber, non-zero, and then applying log P of U, and then away from P, I apply the valuations VLQ and multiply by this weighing factor here, right? And then you can show that this gives you a functorial theory without going into details. But on an abelian variety, well, the obvious thing to do is just to require that all of these ingredients are canonical. So the log function and the valuations are all canonical, and then you get a canonical P-adic height. And that's precisely what happens. For that, again, you need to fix a good curvature from alpha for P. Then, so a P-adic Adelic metrized line bundle on an abelian variety is canonical if all the data in here is canonical. Yeah, so log LP is alpha canonical, means it comes from alpha, and away from P, all the valuations are canonical. Yeah, and so these, as I said earlier, the valuations, canonical valuations, are uniquely determined by L. Excuse me. All right. So if you take everything together, then sort of straight from the definitions, we get that HL bar, so the p-adic height with respect to a canonical Adelic metrized line bundle, is always a quadratic function. Yeah. So it's the sum of a quadratic form, a linear form, and then something constant. But if you just restrict to even line bundles, then you get a quadratic form, and to odd line bundles, then you get a linear form. And well, we have several comparison results, and well, some of them are still in progress, but at least for Jacobians, we can show that we recover the Nekovar height, more precisely the Coleman gross p-adic height, which in this situation, with some good reduction, is equivalent to the Nekovar height. Yeah, and so we're working on sort of other comparison results. We can also show that we recover a Néron-Tate height pairing, if you've seen this before. Right. So let's talk about quadratic Chabauty. Is there a question at this stage? Or, I mean, of course, I'm also happy to answer questions after the talk.
Can I ask a silly question about the Adelic metrized line bundles? Like, to what extent, like if I fix an L, how much choice do I have in L bar?
A lot.
None at all? Or...
Okay, so if you want the canonical one, then there's somewhat less choice, but otherwise, I mean, these log functions are somewhat, I mean, they're fairly flexible, sort of going back. So just for the component at P. Yeah, so even if I fix a curvature form, then there's going to be a log function with that curvature form, but it has also some degree of freedom. Yeah, so there's quite a bit of choice.
But if I restrict to canonical ones, is there only one choice, or?
No, there are. Yeah, so if L happens to be even, yeah, then there's only one having a specified curvature form. If L is odd, then you have more freedom. So so that's for goodness. And then for canonical, there's only one choice. Sorry.
Oh, okay. Awesome.
Yeah.
Thank you.
Yeah, thanks, David. Right, but again, canonical is with respect to this alpha. So there is a degree of freedom in the sense that you fix a good curvature form on the Poincare bundle. Equivalently, you fix a splitting of the Hodge filtration, as in other constructions of the height. But once you have made that choice, then there's no degree of freedom anymore.
Awesome. Thank you.
All right, then in the last few minutes, I will say how we can apply this to quadratic Chabauty, and I guess I have to be a bit sketchy, but that's okay. So the setup is as follows. So remember, we wanted to compute rational points on curves. So X is going to be a nice curve over Q of genus G greater than 1. And I'm going to assume that there is at least one rational point. For explicit methods, you actually need to assume that you can find it, but that's typically fine in practice. I'm going to assume that the Mordell rank of the Jacobian is exactly equal to G, and I make the very strong assumption that the Picard number of the Jacobian is at least 2. And this is crucial. I'm also going to make a harmless assumption that the abelian logarithm, when you look at J of Q tends to QP, that gives you an isomorphism with the tangent space. But that's fine, because if this does not hold, then it turns out you can apply classical Chabauty and Coleman. So for explicit methods, this is actually no condition. And so the goal was to construct, sort of extending Chabauty-Coleman, to construct a locally analytic function f on X of QP, which vanishes in the rational points, which only has finitely many zeros. Yeah, and so that's what we want using this kind of data. And we do this as follows. So we're going to fix a base point B for the Abel Jacobi embedding that I'm going to call I. And we fix a good prime P. We fix a branch of the p-adic logarithm, log QP. We fix an Adel class character with values in QP, and we fix a good curvature form alpha on the Poincare bundle. I mean, you don't have to worry about these choices here. Any choice will work in theory. Right. And using that data, we just defined canonical Adelic metrized line bundles. Yeah, so once I start with an L, I get a canonical Adelic metrized line bundle on where L is a line bundle on J, but I want very specific Ls, namely I want line bundles that pull back to the trivial line bundle, but whose classes are non-trivial themselves on the Jacobian, yeah, in the Néron-Tate group. And because my assumption is the Picard number is at least 2, I can actually do this. Yeah, and this is sort of the same assumption that all quadratic Chabauty constructions have. And I will use the height with respect to this line bundle to write down my function. Yeah, so I can pull back this Adelic metrized line bundle to the curve, and then L pulls back to OX, and well, the log function and all these valuations, well, they pull back to something, and so I'll call log P the pullback of the canonical or alpha canonical log function log LP, and VQ for Q not equal to B is going to be the pullback of VLQ. Yes, this now lives on these functions live on OX, right? And so so that's particularly nice. Remember our height, if I go back here, so this height was defined by choosing a vector above a point X. But I mean, if the line bundle is OX, then there's a very consistent way to do this. I mean, you just choose the canonical section 1. Yeah, and so if I take a rational point X on X, then the height HL bar of I of X, so now this lives on J, well, it's the same as pulling back my Adelic metrized line bundle to X, and then applying the corresponding height there. Yeah, that has a particularly nice decomposition. Yeah, namely on the right hand side, you really just have functions on X. Yeah, so log P composed with 1, and then, well, the same for the valuations away from P. Yeah, and so that's great. I want to use that to cut out the rational points, or to somehow identify the rational points among the p-adic points, because this is somehow a relation satisfied by rational points. And so this log P composed with 1, that's already defined on p-adic points on X. Yeah, so I want a function, locally analytic function on p-adic points. The left-hand side is only a priori well defined on global points, but it turns out that you can extend this left-hand side, so extend HL bar to a locally analytic function on QP points. Well, I meant to say a bit more about that, but suffice to say that you can do this because of our assumptions, because the logarithm gives you an isomorphism of J of Q tensor QP to the tangent space, and because the rank is equal to the genus. That lets you do this. You can write HL bar in terms of abelian logarithms and products of abelian logarithms if you want. All right. So this means that I get the local analytic function f by defining it as HL bar composed with I. Yes, so minus log P composed with 1, right? I mean, this here is automatically defined on X of QP. And then, well, yeah, I mean, I pull back this extension of HL bar to the curve. Yes, this is a locally analytic function from X of QP to QP, and it satisfies the nice property that I know what it does to rational points, right? Because that's how I defined f. I know that when I evaluate in a rational point X on X, then, well, what I get is the sum of all the local heights away from P, right? Because HL bar composed with I, that's the global height. I subtract the local height at P, and so I get the sum of all the local heights away from P. And this function has two very nice properties. First of all, I mean, I can sort of predict what kind of values this function takes on rational points, because I can restrict what VQ of 1, what kind of values this will take on Q-adic points for all Q not equal to P. And it's actually trivial for almost all of them, certainly for primes of good reduction. And this is not so hard to see. I mean, you can show this function factors through the reduction graph if you want. Yeah, and then the only thing left to show is that this f actually only has finite fibers. Yeah, so for every t in QP, there are only finitely many points mapping to that. And so if you take all of this together, we get a function f whose values, well, which will take values in some finite set. Yeah, then for each element of that finite set, I know there are only finitely many pre-images. So if I can make all of that explicit, yeah, if I can write down f, if I can write down all these possible values of that f can take, yeah, then I can use this theorem to actually compute the rational points. Yeah, just by computing all of the elements x, all of the points x, such that f of x lives in the set of sort of allowed values here. Yeah, and so that gives you a way to somehow write down a finite set of p-adic points that must contain the rational points. And there are several methods to actually from that find the rational points precisely. Yeah, and I was going to say a bit more about the proof here, but given the time, I think I will stop here, and thanks for your attention.